in the last lecture about tabulations of thermodynamic data. Now let's have a look at kinetic data. And one of the problems with kinetic data is that it's even less consistent than thermodynamic data. So there can be real problems with thermodynamic data. And there's a process which is called evaluation, which is the examination of the available rate data from the literature and the recommendation of rate parameters. In addition, and increasingly importantly, there's the compatibility with experimental global observables. And we'll talk about that more in the next lecture. Okay, so there used to be significantly more evaluation of rate data than there is now. And this is one of the last tabulations, one of the last evaluations, and it was 13 years ago, or it was published 13 years ago. And this man, colleague of mine, Don Balch, was an important person in the development of the whole methodology of evaluation. So let's see what lies behind this process. So the next few slides show the structure of a typical data sheet. So the way in which these evaluations occurred was a group of grey-haired old men, and it was just men, would get together and discuss the available rate data. And Don Balch's group would produce tabulations of all the references we should be looking up. And we would then sit back and stroke our chins and decide what sort of values to recommend for these rate constants as a function of temperature. And so this is the structure of a typical data sheet, and in this case for O plus OH going to O2 plus H. And it starts off with the thermodynamic data. Now, this is not the right place to go to for thermodynamic data because, as I say, it's a little old. But for these species, it's not going to be bad. But first of all, a tabulation of thermodynamic data, and then a tabulation of the available rate constants from the different groups around the world, and then reviews and evaluations of the data. So these are reviews and evaluations dating from 1992 to 1997. So it provides the rate coefficients. Some of them are at single temperatures. Some of them show temperature dependencies explicitly over this temperature range. And then similarly for the evaluations, it shows the temperature ranges involved, the reference, and then references to some comments, links to comments, which come down here. So this is an example of a set of comments. So talking about determination E here, says fast flow system in which OH radicals were created by pulse laser photolysis of nitric acid in the presence of much higher concentrations of oxygen atoms, which were previously produced upstream of the HNO3 injection by the N plus NO reaction. OH was monitored by LIF, and the time delay between the pulse generating the OH and the LIF probe was varied. So this is related to one of the methods that I showed you on Tuesday for this specific reaction. Then F refers to this evaluation by Joe Michael, in which he's calculated the data from thermodynamic data using this reaction here. So he's taken the rate constants for H plus O2 together with thermodynamic data and calculated the reverse one. And then, etc., an expression from Lewis and Watson adopted for low temperature range. again from this H plus O2 reaction here. So that's a set of comments. And then here's the result of the evaluation. So one of these grey-haired men has made a suggestion as to what this rate constant should be. People have sat and discussed it and agreed on it. So that's the recommended expression over the range 250 to 3000 K. And this is the reliability, delta log K. So this is basically an uncertainty of something like 70% in the rate constant. An important point is that that is not a truly statistical determination of the uncertainty. It's basically a guess at it, just looking at the data. And we'll come back to the deficiencies in that uncertainty later on. And then some comments. So the only direct studies of this reaction have been carried out at low temperature, where there's excellent agreement among the most recent of them. No direct measurements above 515 K. But what you can do is you can use the reverse rate constant, H plus O2, together with well-established thermodynamic data to get that reverse reaction. And the reaction's been subject to a number of theoretical studies: Miller, Troy, Harding, Troy, and Ushakov. And finishes up with an Arrhenius plot. Here's the reverse reaction. So there's the recommendation for the reverse reaction. The uncertainty, now delta log K is only 0.1 at 800 K, but rising to 0.2 at 3,500 K. No direct determinations below 500 K, so this is the reverse of what's going on there. So the low temperature range is determined, well, they only go down to 800 K in this recommendation, but you can determine it lower down by using the reverse reaction. And there's the data. That's a mass of data. You can't see anything there, all these determinations. That tells you how extensively this reaction between H plus O2 has been studied and the relatively small deviations from the recommended rate constant. And what you can see from this is that what you could do, and we'll do this later on, is you could put upper and lower bounds on the range of possible values simply by taking the upper and lower bounds of these experimental determinations. And a reminder of an earlier slide on H plus O2 from a relatively small number of determinations in a paper by Hong using shock tube measurements, and also a reference to the discussion of this reaction by Burke, which is significantly later than what we were talking about in this evaluation. So this comes from Hong in 2010. So these data were not included in that evaluation, but this is a subsequent evaluation that's been updated by Burke here. Okay, now here's an example of a reaction which is much fewer data available. And the experiments range from 300 K using a reaction, a situation where you look at this reaction in comparison with a reaction between CH3 plus CH3. And these rate constants here depend on the value used for CH3 plus CH3. And at the time, which as you can see is an awful long time ago, there wasn't good agreement about what that value for CH3 plus CH3 would be. If you take the most recent value and re-evaluate their data, then you get agreement on 7 times 10 to the minus 11. And then these high temperature values up here, and the shock tube measurements are fairly old, and they used mechanisms with several steps in literature rate data to determine the rate constants. This raises an important issue which has still not been solved. What would be good would be if we supplied our raw rate data. We supplied our measurements directly. And this isn't unreasonable. We could supply the decay curves if we're using pulse photolysis or the direct measurements made in the shock tube. And then what could happen is they could be reevaluated as our understanding of associated reactions that might be involved in some minor role in the determination. As those get reevaluated, we could change the recommendation. And if you look at X-ray data, for example, that's a bit of a jump, but if you look at X-ray data, then people who publish structures are required to provide a link to their raw data so that those X-ray data can be reevaluated. So if they're going to do a publication, then they have to provide the raw data before they're allowed to publish those results. And we should really be doing the same in kinetics. Because of the uncertainties, because of the difficulties of making kinetic measurements, we ought to be providing those raw data so that people can come along later on and reevaluate them. But we don't do that as yet. And it won't happen, I don't think, in my lifetime. So here's the recommendation, 1.2 times 10 to minus 10 over this range, with an uncertainty rising from a factor of 2 at 298K to a factor of 5 at 3000K. Comments: considerable scatter in the data. References 1 and 2 were derived from very similar studies. Need correction for the value of the rate constant for the methyl radical recombination used in the simulations, and that was done in the evaluation. And the reactions presumed to proceed via an ethyl radical adduct. So what happens is triplet CH2 and CH3 come together, they form ethyl radical, and then that falls apart. As a result of that, there's going to be a very weak temperature dependence for this reaction, because it's essentially an association reaction followed by dissociation, an exothermic dissociation. May suggest a very small negative temperature dependence, but scatter at high temperatures large, and provisionally a temperature-independent rate constants recommended with substantial error limits. If you have pressure-dependent reactions, then what was used in this evaluation was this Troe fitting method, if you remember, in which we take the Lindemann-Hinshelwood expression for the rate constant and modify it with this parameter f, and then you have Arrhenius expressions for K0 and K infinity, the low pressure limit and the high pressure limit, and you fit f cent to something of this sort. And so this is H plus C2H4, the pressure-dependent reactions. So K0 for M is equal to helium over this temperature range, for M is equal to nitrogen, and then K infinity expressed in this form. And then FC expressed in a slightly reduced form compared with what I showed you on the previous slide. And there are the reliabilities. Delta log K factor of 2 over that range, similarly for K infinity, and then uncertainty of 0.1 in delta FC. So that's the way pressure-dependent rate constants are tabulated within this evaluation. And there's the data for H plus C2H4, and there's a plot of K infinity. So here's the association reaction at a range of temperatures. Now, a group in Hungary decided that this rather ad hoc way of assessing uncertainties was really not good enough. As we'll see tomorrow, if you want to compare a mechanism with data, for example, for ignition delays or shock tube measurements of ignitions, then you need to be able to estimate the uncertainty of the rate parameters you put into the model, because then you can estimate the uncertainties in the model that you need to you need to determine the uncertainties in the rate constant you put into the mechanism, so that then you can determine the uncertainties in the overall model that you're comparing with experiment. And you can't really do that with these rough estimates, because it turns out they're really too big. And they don't help to constrain the model as well as they should. And so this was this group in Hungary who developed analytical expressions that describe the temperature dependence of the uncertainty in K as a function of the elements of the covariance matrix of the Arrhenius parameters. What we said was that if you take a modified Arrhenius expression, a t to the n e to the minus e over rt, then there is a strong correlation between the parameters there, especially between n and e, but also between a, n, and e as well. So, so what they did was to start to look at this covariance matrix, and they made recommendations for an improved representation of the uncertainty information in future chemical kinetics databases using the covariance matrix of the Arrhenius parameters. And the methods suggested for determining the covariance matrix and joint probability density function of the Arrhenius parameters. So this is an important paper, and it's followed by a subsequent important paper that I'll give you later on. And then we'll use the results of these things or we'll discuss the use of the results of these tomorrow, maybe even later on today. So O plus C2H4. So here's the rate data. Here's the evaluation, the Bolch evaluation. So there's the rate constant over the range 220 to 2000 K. The uncertainty being estimated as 0.1 over the initial range 300 to 1000 K, and then 0.3 from 220 K to 2000 K. Sorry, that should be 1000 K up to 2000 K. Okay, so this is what this looks like. So there's an uncertainty at 200 K of 0.3, an uncertainty over this range of 0.1, and an uncertainty at that temperature there of something of the order of 0.3 again. And this is an attempt to represent that as a function of temperature. And you can see that there are real problems in that, and there must be a better way of doing it. Here's CH3 plus H going to singlet CH2 plus H2. So there's the rate data. Here are the estimates, comments on the preferred values, etc., etc. Shock tube studies are in reasonable agreement with combining thermodynamic data with low temperature data on the reverse reaction, singlet CH2 plus H2, whereas the value for K obtained from a flame study of those seems unacceptably high. So uncertainty, the reliability, 0.15 over the range 300 to 1000 K, 0.3 over that range 1000 to 1700 K, 0.2 over that range. So problems in the middle range because there aren't very many determinations, not bad at low temperatures, not bad at high temperatures. And so what they do is they start to use this uncertainty matrix here, this correlation matrix, where these are the determined variances for the rate constant for A, for N, and for the activation energy. And these are the covariances over here. And then what they can do is they can say, let's define the uncertainty now statistically in terms of this matrix. And this is a definition of that uncertainty in terms of the the variances themselves, but also the covariances here. And this quantity m depends upon whether you want to make that uncertainty 3 over log 10 or 2 over log 10 in your definition of the reliability of the evaluation. And so this is CH3 plus H going to singlet CH2 plus H2. And just let's read what they say at the bottom here. Uncertainties of reaction R5 are defined in 3 temperature intervals, that one, and that one, as we've just seen. And the uncertainty temperature function here was fitted to the values represented by the circles. So here's a fit to those circles. The best least squares fit doesn't approach these points well because the recommended uncertainties simply weren't consistent. The alternatively proposed f of t curve, this dotted line, remains below all the uncertainty points as the highest average value for sigma squared in the inverse temperature interval that. So what they're doing is they're recommending that what you should do is to use this uncertainty range defined down here. And we'll come back to this later on. And so this is another paper in which what they did was they looked at important elementary reactions in hydrogen and syngas combustion systems. So this is H2 plus O2 and H2 plus CO plus O2. And they re-evaluated the uncertainty of the parameters for 22 reactions using all the available experimental and theoretical data based on log A, N, and E. So they're not using the Balch determinations now. They're starting from scratch. And they stored this as a covariance matrix in the uncertainty range and placed symmetrically about the mean rate constant. So what they're doing is they're looking at those determinations. They're looking at the best fit to those determinations, and then they're looking directly at the scatter around it. Now, there are problems with this because what you ought to be doing is weighting those rate data in some way. And it's difficult to do that except using what the original experimentalists suggested should be used. So they discuss the uncertainty of the backward rate constant using thermodynamics and provide a set of software tools to allow the approach to be applied to any set of measured and calculated rate constants. So any of us could go along, use this methodology, and then get the uncertainties. And so here are some examples of the uncertainties that they showed. CO plus HO2, an uncertainty of 0.7, HCO plus H, coming down to O plus H2 with this temperature-dependent uncertainty here, and these other determinations down here, where the uncertainty ranges are very much smaller than was the case in those original evaluations. Okay. Any questions on that? So what we ought to take out of that is that these evaluations exist. They are a good source of experimental data, but they aren't really the best source of the best recommended values together with the uncertainties for those recommended values. And over the last few years, much better ways have been developed for determining the rate constants themselves, but also the uncertainties. Again, based on experimental data. Okay, so let's move on. Let's have a look at chemical mechanisms. So really, this is where much of this lecture course has been aiming. In combustion, you want to use chemical mechanisms, and you want to use them to put into a model of an engine, or you want to use them to help you understand your ignition measurements or whatever. So the chemical mechanisms are the way in which chemical kinetics gets into combustion. So the chemical mechanisms are central to the overall process. The rate data that goes into them is important. And that's what I've been trying to discuss over the last few days. But it's really the end product is actually these chemical mechanisms. So we're going to examine ways in which mechanisms are constructed, their dependencies on rate and thermodynamic data, their evaluation using experimental targets, and optimization of component rate constants using direct and indirect data. So that's a key thing. So far, we just talked about what we might call direct data, direct measurements of rate constants. But indirect data, measurements of ignition delay times, et cetera, do in themselves provide quite a lot of information on kinetics. And so that's what we're going to look at later on in this lecture, this part of the lectures. Okay, a reminder of this. This is taken from a paper by Ed Law that was modified last year, or slightly extended last year, by Fei Qi's group in China. And what it shows is the number of species and the number of reactions in a wide range of chemical mechanisms. And there are thousands and thousands of reactions and rate constants that we need for these models. Some of them, these rate constants are not going to be desperately important. In other words, the combustion system may not be very sensitive to them, but these are the sizes of the mechanisms that people are constructing and using nowadays. So, how do you construct a chemical mechanism? And a hierarchical approach has been used and proposed for many years now. And this was seminal work by Westbrook and Dreyer, construction of comprehensive hierarchical chemical mechanisms. Build up the mechanisms with increasing complexity. So O2 reacting with H2, and then with CO and water, CH4, etc. Using, at that time, evaluated data where available. And so these are examples of hydrogen-oxygen mechanisms. So this is Li et al. 2004, and based on an earlier mechanism by Muller. And this has been updated by Michael Burke in this paper in J-Chem Kinetics. Konoff, Combustion and Flame, 2008, examines the uncertainties of the rate coefficients based on an earlier 2004 mechanism. Hong et al., we've seen work from Hong et al. on a reaction recently, Combustion and Flame, and then Karomnes. So these are 4 mechanisms which are still used, especially these Karomnes and Konoff mechanisms. These mechanisms are then tested against global observables. So this is the mass burning rate, and this is the ignition delay time. And so these are simulations of those processes based on the mechanisms. So the dotted lines are the original Muller mechanism, and then the full lines, the Li mechanism, which is a modification of it. And similarly here, for these ignition delay times for hydrogen, oxygen, argon in shock tubes. So the group has made these determinations in shock tubes of these delay times, and then run the mechanisms and compared the two. And you can see the agreement is really quite good. And so this is Hong. So we've looked at these data before, H plus O2 going to OH. So he's revising the mechanism using these shock tube data and revising it specifically for the H plus O2 reaction and the OH plus hydrogen peroxide reaction with the data here. So And you can see that there are quite significant changes in the value for this rate constant here. And these are OH concentrations using the current mechanism in red, and then some earlier mechanisms, and similarly over here for the species profiles. So these are the sorts of modifications and updatings and tests that go on in this field. So I mentioned the other day that this H plus HO2 reaction is really very important and has high sensitivities in the hydrogen-oxygen system. And the complication with it is just what are the branching ratios. So the reaction can produce hydrogen H2 and O2. It can produce two OHs, and it can also produce O plus H2O. And depending upon what the branching ratio is, this reaction can be either reducing the rate of the hydrogen-oxygen ignition or increasing it. And so these are examinations by Burke of the branching ratios for this reaction that are pretty key. And here's a sensitivity analysis from him, looking at the sensitivities in this paper with respect to so these are different burning velocities, ignition delay times, hydrogen concentration. And you can see here's the effect of this channel, H plus HO2 going to H2 plus O2, which decreases these, the burning velocity and the ignition delay time, but actually increases the amount of hydrogen that's formed for obvious reasons. So that's one of the channels. Here's another one, H plus HO2, higher sensitivities for burning velocities, and this negative sensitivity for producing H2, again, for obvious reasons. So branching ratios here are very important. So it's not just the overall rate constant, it's the branching ratios that play a key role. This is a very, very substantial analysis of going further. So we've talked about hydrogen, oxygen, and this is going further and looking at a wide range of fuels and evaluating mechanisms using ignition delays, laminar burning velocities, and flame speeds. From looking at these determinations from shock tubes, jet-stirred reactors, flow reactors, flame speeds, and flame speciation. And so these are examples of sensitivity analyses. So this is the laminar flame speed for methanol, looking at the sensitivities, excuse me, looking at the sensitivities with respect to various reactions. This is looking at the recommended rate constant that they've given for CH3 plus OH based on various determinations at high temperatures. Looking at the sensitivity to thermochemistry. So, so this is the sensitivity with respect to the entropy of oxygen. So the entropy of O2 has a very, very high sensitivity coefficient in this thermochemistry, in this laminar flame speed determination. For CH3, the sensitivity, high sensitivity with respect to the enthalpy of formation for CH3. And interestingly, for CH3O2, it's mainly the entropy again that's sensitive. And finally, here are the reaction channels. So CH3 plus OH is a complicated reaction. So what happens is CH3 and OH come together to form methanol, but then what happens is this energized methanol can fall apart in a variety of ways. It can fall apart to form singlet methylene plus water, to form CH2OH plus H, to form CH3OH itself, formaldehyde plus H2, CH3O plus H, and and this species HCOH plus H2. And these are the reaction channels that have been determined theoretically and what they're recommending from this analysis over here. So that's going to much more complex systems and using the mechanisms that are available there and comparing them with these experimental determinations. Even more complex mechanisms, C1 to C5 alkane combustion, high pressures, and these are determinations coming from Galway. Anybody going to Dublin? Nobody's going to so you're going to Dublin. Only one of you is going to Dublin. That Dublin conference is being run by this Galway group, but not in Galway. Dublin is much easier to get to than Galway. So this is mixtures of methane, ethane, propane, butane, normal butane, normal pentane, studied in the temperature range 630 to 1550 K, pressures 8 to 30 bar, equivalent ratios of that, in a rapid compression machine and a shock tube. And the mechanism they use is this one that was constructed at Galway. There are more recent developments we shall talk about later on. Even more complex mechanisms, this is dimethyl ether from a few years ago. So this is 2000. And very little was known about, so this is oxidation of dimethyl ether. Just let's look through it. So this is the radical, which is formed by abstraction by OH from dimethyl ether. That can fall apart to form formaldehyde and methyl. It can react with O2 to form this peroxy radical. So this reaction in reverse there. And that can isomerize to form this hydroperoxide. And this hydroperoxide can dissociate, but it can also add another oxygen. And this forms this species here, which is crucial in, as we'll see tomorrow, in determining the branching of this system here. And one of the problems with constructing this mechanism in 2000 was that very, very few data were available. And so what they did was to make estimates of the rate parameters using, by correlating rate constants with thermodynamics. But we'll see a fuller discussion of this in topic 7. So that's one of the problems associated with a mechanism where you don't have very much rate data available. You've got to start making estimates. Nowadays, many more of these will be calculated if they hadn't been measured. So these are large molecules. Again, how can we provide data that can be used for improving the mechanism? And so these are experiments from China using a heated reactor that we talked about in lecture 2. So this is a reactor that can go up to between about 1,000 and 1700 K. There's a bit of a gradient along the reactor, but that can be accommodated. And so you send the gas in there, and it either dissociates. So this is a pyrolysis reaction, cyclohexane pyrolysis, or you could do an oxidation reaction in it. Then the great thing that you can do is you can use synchrotron radiation, synchrotron VUV radiation to do photoionization mass spectrometry. So you have a pinhole, a skimmer, and then you send the VUV light through and then send it into a time-of-flight mass spectrometer. And with this, you can see an awful lot of compounds because you've got tunable radiation and also time-of-flight mass spectrometry. And so this is the sort of data that comes out of it. Open symbols are experiment, full lines are simulations based on the mechanism. The mechanism is based on earlier work in Hefei, which is where the Feiqi's group was based. and so it's based on that down there. And you can see the comparisons with this wide range of data. So there's the cyclohexane decreasing, and then methane increasing, methyl radicals being formed, various hydrocarbons here, and also radicals, C3H3, the propargyl radical. So a phenomenal amount of data are available to compare with the mechanism. And so this is really providing very good tests of the mechanism. And this is, from the mechanism, this is what's called a rate of production analysis, which is quite a nice way of understanding what's going on in the mechanism. So you're starting off with cyclohexane here, and it can do two things. It can ring open, or it can lose a hydrogen atom. The mechanism says that at this temperature, 36% is going in this direction, 64% in that direction. You produce this radical here. That can either ring open, or it can lose a hydrogen atom and form this, six-membered ring alkene. So cyclohexene, and you go on down this route here with quite low probability there. And what's more probable is that it ring opens and loses a fragment. So this is forming butadiene and losing ethene. So it's forming ethene and butadiene 90% of the time. And then we can go over to this 1-hexene here, which primarily falls apart to form these two allyl radicals there, which in turn can react in a variety of ways. So the thickness of the arrows denote the relative rate. So the great thing about this determination is that this has all been checked against these very detailed measurements using VUV radiation to ionize the reactant and the products. So this is methyl cyclohexane, so another going up one, again using synchrotron radiation, and these are the determinations in this case. The mechanism is based on the cyclohexane mechanism, and development included theoretical calculations of abstraction by H. So not only have they used these determinations, they've also used theoretical calculations to improve the mechanism. Let's mention a couple of big mechanisms that are provided in the web. Does anybody use Aramco? Nobody uses the Aramco mechanism. Okay, so so the kinetic and thermochemical properties of a large number of C1 to C4 based hydrocarbons and oxygenated fuels over a wide range of experimental conditions. And it's developed by the group in Galway again. Developed in a hierarchical way from the bottom up, the way we've talked about, H2 plus O2, followed by a C1 submechanism, testing all the way as you go along, and then introducing these C2, C3, C4 species. And oxygenated species including formaldehyde, acetaldehyde, methanol, ethanol, and dimethyl ether. And validated against a large array of experimental data, including data from shock tubes, rapid compression machines, flames, jet-stirred reactors, plug flow reactors, etc. And so here's a whole host of references to that Aramco mechanism. And there's a website in Galway that's given there. So you can, if you're interested in these big mechanisms, then you can check it out there. Another one is the USC mechanism. So this was developed in Hai Wong's group before he moved to Stanford. And this incorporates recent thermodynamic, kinetic, species transport data, C1 to C4 hydrocarbons, developed based on optimized H2CO combustion, GRI mech, which we'll talk about later, and then comprehensive mechanisms for ethene and ethine, and then for C3 and 1,3-butadiene combustion. And then validated again against ignition delays, species profiles, etc., 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 etc. So those are two big mechanisms that you can go and check. Now, just let's have a look at this at GRIMEC. So you check where we're going. Okay. So, has anybody used GRIMEC? Yeah, so quite a few people have used GRIMEC. And so, it's a list of elementary chemical reactions and associated rate constant expressions. And they've used, it's for small species, and they've used, and mainly methane, used sensitivity tests against target experimental data to allow the selection of rate parameters for tuning. The key thing about GRIMEC is that it's a tuned mechanism. So they've varied the parameters within uncertainty ranges until they get the best fit. The process of automatic simultaneous parameter optimization to get the parameter set for each successive release of GRIMEC, strict constraints keep the rate parameters within predetermined bounds based on evaluation of uncertainties, applications of conventional reaction rate theory. So it's optimized as a whole, and substitutions and further selective tuning shouldn't be done. So if you go through that and you find that you think one of these rate constants could be represented in a better way, then you shouldn't change it because this whole mechanism has been tuned. All the reactions are treated as reversible thermodynamic data based on NASA and Technion's provided. Input files feed directly into ChemKin. GRIMEC 3.0 is 53 species, 325 reactions. It's optimized for methane as a fuel, but it does include C2 and propane chemistry. It's optimized against chosen targets in the ranges T equals 1,000 to 2,500 K, pressure of 10 torr to 10 atmospheres, and this range of stoichiometries. And you can find information again down here. So this is an example of the optimization process. So the bold reactions are the ones that they decided should be optimized. So they looked at sensitivities and decided that these are the reactions that could be optimized. And the ones in red are the ones whose active parameters were changed as a result of the optimization. So the bulk of these weren't changed, but you can see there that H plus O2 plus water going to HO2 plus H2O was changed. And this is related to what we were talking about a couple of days ago. Water is a particularly efficient third body, and they found that that this was an appropriate one to tune because there was significant uncertainty. But even so, they only changed it by a factor of 1.2 from the recommended value. So there is tuning going on, and you can click on a reaction number and find information when you go to the website. And here's the thermodynamic data for reaction 35. Again, you can check that against ATCT, for example. And here's the optimization process. So these are ignition delay times from Seary and Bowman. So these are the experimental determinations. This was an earlier version of GRIMEC 1.2. And here's GRIMEC 3.0, the most recent determination. So although these GRIMEC is optimized, it's obviously not going to reproduce every set of experimental observations exactly. So even when they optimized it in GRIMEC 1.2, they were missing these data by a fair amount in their optimized values. But that was improved in GRIMEC 3.0. And here's a simulation of an OH concentration profile in a shock tube study, CH4 O2 argon at 1778 K, and you can see that it doesn't reproduce it exactly. There is some difference between it, but that's the best simulation coming from GRIMEC 3.0. Other examples of tuning, methane, air, flame speeds. These are CH concentrations, mole fractions in a flow tube study from Peter Glaborg's laboratory, and then these are ignition delay times again. So those are examples, and you can find all of those on the website. Now, I talked earlier on about the need for us to make our data available. And this is something that Michael Franklak at Berkeley has been very keen on for some time. Not only making the data available, but interacting so that we agree what's the best data set and set of test data that we can use. So in 2007, at the Combustion Institute, Michael discussed the future of predictive combustion models through what he termed process informatics, which relies on three major components: proper organization of scientific data, availability of scientific data tools for analysis and processing of these data, and engagement of the entire scientific community in data collection and analysis. It's a great objective. It hasn't really happened yet. And so here's the current site, which is no longer in Berkeley. So there's a depository and a library. So the depository is a repository of data provided by the community. The only requirement is that there is data record completeness, which is checked electronically for use in the data schemas. And the library is a set of data evaluated by the prime work groups, which I'll show you in a minute. And a set of prime kinetics codes is being developed to assist in both initial submission and evaluation of the data. And so there are a whole set of different groups. So C0 to C2 is an analysis, is a group that's looking at the rate data for species up to ethane and ethene and acetylene. So these are rate data involved in C0 to C2. And hydrocarbon pyrolysis and oxidation. And then these are bigger species, C3, C4, hydrocarbon, oxidation, C5, 16, etc. And along you go. And then these are other groups. And you can see that some of these groups are big. Sort of the sooting group is big. And Michael Franklak is particularly keen on sooting and has been able to persuade people to get involved. But the quantum chemistry group is really very small. There are some people involved in transition state theory calculations, etc. So this was a really very determined attempt to involve the community as much as possible. But the community hasn't really, you can see the numbers of groups is not as large as it should be. Okay. I think I'm going to let you off for 5 minutes. Does anybody have any questions, any comments?
When we want to verify a mechanism based on ignition delay time, in the experimentation we have shock tube and RCM. But the ignition delay time for these two facilities are not the same for all the cases. What's the reason for this difference?
So why do RCMs give different results from shock tubes?
Shock tube and RCM.
Yeah. Does anybody Can anybody answer that question? I mean, under exactly the same conditions.
Exactly the same condition, the same fuel, but the effect of diluent, for example, argon, on propane in RCM and the shock tube is different. For one, it accelerates the ignition. For the other, it makes it to be late.
Okay. Have you done simulations of them both?
No.
Because I mean, one of the issues is I mean, there's physics going on as well as chemistry, and so the physics that's going on in the RCM is undoubtedly different from that in the shock tube, and so when you put that physics into the simulation, that may in itself lead to differences, but.
So which one should be our reference?
Well, I don't think. I mean, it could be either. I mean, the main thing is when you do any simulation, you've got to get not just the chemistry right, but the other processes that are involved right. And I'm not going to say anything. I'm not going to commit myself as to which I think would be the more reliable. But you've got to make sure that you know. It's not just the chemistry you're simulating; it's the physics as well. That's a mealy-mouthed reply, but. Any other comments? Yeah.
So another thing is for the ignition delay, the experiments themselves, the interpretation is different between.
Sorry, could you say that again?
For the ignition delay between shock tubes and RCMs, the interpretation is different. The time zero is different, and therefore the quantity of ignition delay
Okay.
needs to be different across papers. But that's what I saw.
Okay. Have you simulated them?
I'm not simulated, but I've done experiments on continuous flow reactors, a different
And-
regime.
Okay.
And again, my time zero was different as opposed to any of the other experiments.
Right.
So
Okay.
that made a huge difference with respect to the value.
Yeah. Yeah. And how different were the time zeros compared with the ignition delay? I mean, what fraction of the ignition delay was the change in time zero?
I think it was, it depends. Mine was a non-premix system, so the RCMs and shock tubes are premix systems. So for shock tube experiments, when the shock went past their measurement location, that was their time zero. And for different experiments, it was for like RCM, based on when they had the peak temperature, that was their time zero.
Mm-hmm.
So depends.
Okay.
That's what I observed.
Yeah.
So a couple of papers had, because RCM has a temperature rise, then it drops again.
Yes.
Their peak temperature was their time zero, although the temperature drops beyond that. So,
But presumably, when you do a simulation, then you would incorporate those effects in the simulation. Okay, so I presume you're going to go and enjoy yourselves now, are you?